Thank you, Tian, and thank you, Hong Tu, for organizing. Thank you, Philip and crew, for all your help as well. It's been really great so far. So when I was thinking about my lightning talk, I asked Hong Tu, what should I talk about? And he gave me 4 questions. And being a very literal guy, I took those 4 questions and made 4 slides, each answering 1 question. So it's going to be very different from the other ones. No fancy images or equations, just maybe sort of high-level thoughts about these 4 questions. Let's see here. The suspense is killing us, right? What is he going to say about these 4 questions? And what are the 4 questions? Ah. Yeah, these are the 4 questions, by the way. Thank you. So I can just go forward like this. All right, so I'll get to these 4 questions as we move along. But so the first one was really about what would be the next stage of research in this field for the next 5 to 10 years. And so again, my focus is, I do a lot of imaging, but primarily it's neuroimaging, and primarily it's functional neuroimaging. So most of my focus is on that area. I think one of the big things that what's happening right now in the field of neuroimaging is sort of the transition to the era of big data. So Hong Tu really nicely talked about that. There's these biobank-sized data sets. It's sort of changing the paradigm. Usually people had 30 subjects if they're lucky, 50 subjects, and they, even if the correlation between some trait and brain volume was, say, 0.15, because it was so few people, the sampling distribution was so wide, so they were getting sort of correlations of 0.9, and that's what Nature and Science decided that you have to have that to publish it. But it's sort of driven by noise. And now that we're getting into these biobank size where there's like 50,000, 100,000 people, you're going to get very reliable correlations of 0.15. So they're going to be smaller, but much more reliable than the ones that we've gotten used to seeing. And sort of that's going to sort of have to change our way of thinking about the problem. And also the sort of statistics that we do has to change with that. And so I think we're in a real paradigm shift. And I think Hong Tu's work is a very nice example of this paradigm shift. It's something that we sort of have to sort of move on. And it's going to create a lot of complications. So I'm calling this population neuroimaging. The second thing a lot of people talked about is multimodal data fusion, as I call it. That's sort of one of the things I was sort of complaining to Chen yesterday, that we had these 4 sections: EHR, imaging, smart, computational. It's really one, right? At the end of the day, if we're going to do all this AI stuff, we're probably going to combine all that information into one. So we should really be talking and not siloing ourselves artificially. So I hope we try to avoid that. The third thing is, acquiring better images in shorter time. There's radiation doses, there's patient burdens, there's cost. If we can acquire data quicker, easier, that's something that we're going to be looking to do in the coming years. This is, I think, one of the most critical things. Somebody mentioned clinical application. We're very, very bad at clinical applications, particularly in functional neuroimaging. That was the big promise, right? We're going to read the mind. We're going to understand everything that's going on. It's not that easy, right? And moving from sort of our studies of 30 people in our papers and moving it into the clinic is a huge endeavor. And I'm going to be a little critical of us a little later on and say what some of these things. Understanding individual differences. My brain works different than your brain, right? It's just the way it is. And there's very subtle differences, and sort of understanding that is going to be a complex thing moving forward. And again, as Joan said, brain-computer interfaces and the like are big things. So that's sort of where we're moving towards. I really think this big data, population neuroimaging, fusing data types, and trying to get more clinical applications are sort of some of the big things that we're looking for. Question number 2 was, most exciting and pivotal breakthrough that AI and statistics could change the practice. So I thought a lot about this, and so sort of ChatGPT and those things were real game changers. When I saw that, I was like, wow, how can they do this? And I was thinking, what is it that it's really doing? It's synthesizing information, right? And that's something that we kind of do in neuroimaging as well. Again, we often do we have 100 studies of 30 people of working memory, right? And so how do you synthesize that information? Well, people usually do meta-analysis. So they extract tables from all the different PDFs. They look at where the locations are, and then they try to combine this into something. And that's something that ChatGPT could really do, meta-analysis, right? So if you have, it could find the papers, it could extract tables, it can sort of synthesize these information. So you can imagine a future where you could just ask something about these things, and they could perform meta-analysis. And I also think that there's a way of sort of the idea that we're moving forward is sort of querying brain maps. So if you put in a structural map, you can say, like, well, what's the amygdala volume in this brain map? And comparing it to sort of population norms and things like that. That's also something that a synthesis of information that I think that we'll be looking at moving forward. You could put in an activation map and try to figure out what it is that this person is doing. Do they feel fear? Are they in pain or whatnot? And so you can imagine lots of those different things moving forward. And so I think synthesis is something that we're going to see a lot of. Data fusion as well. I mean, it could be that we have a bunch of different data sets. So, I'm lucky and I have data types A, B, and C. Tian has A and C. Hong Tu has A and B, right? So we want to sort of combine all that data and sort of borrow strength, even though we don't have the same sort of imaging modalities or even data types. Like you could have genetic information, I don't, but how do we, so it's sort of it's different from a missing data problem, it's a missing data type problem, and I think that's something that one can work with AI, and that's going to become very important as well. And then this was another thing, is sort of, it was a very interesting question, about replicability and things like that. These small studies of 30 people are really great for a lot of things because they're very targeted, right? They're targeted with a very strong research hypothesis. Biobank style data is diffuse, right? There's no targeted, it's just there, right? And so the question is, how, but the biobank data has information. We're humans, right? We're all humans, and our brains have certain properties that are sort of common with each other. So what is it that in the biobank data that we can take that can help inform these more clinically targeted things and help, kind of get more refined estimates in these more targeted estimates. And I think that's going to be sort of one of the big research topics. And I think that's something that statistics, you think sort of like an empirical Bayes thing. You're shrinking towards a population average, but you're really trying to also retain the individuality of the 30 people that you're looking at. But I think that so there's going to be a lot of interesting ways of doing that moving forward. And then also we talked about this, developing synthetic data. So, again, can we do sort of fake brain data that can sort of help do this? It's sort of interesting. It's people have tried to make fake brain data, but it's kind of hard, right? You can sort of see when it's wrong, because sometimes you do processing of brain data. You take the brain data is like this like folded scrap of paper, right, that you crumpled up, right, because it's all folding. And then you can, if you take that volumetric data and try to synthesize it, there are pre-processing steps where you sort of blow it up afterwards, and then you can really see when it's synthetic, because it can't handle that curvature that exists very well. So it's actually much more complicated in the brain than it is with real images and things like that. And those are the sort of things that we're going to have to sort of figure out how to deal with. So it's a very complicated problem. And then this was sort of a bigger picture thing. Hong Tu says, think big, understanding how we learn, right? So these algorithms are learning, but we're also learning. And a lot of things that we do, it's like let's say that I'm learning how to circumvent a maze or something like that. I get better and better as I get more information, right? But also my brain is processing it different ways, and sort of understanding how those things go intact, I think, is something that this AI could help a lot with. So those are sort of things I'm sort of keen on. What's the most important research questions? Again, moving it into the clinic. I think if we don't move it into the clinic, you sort of, why? You know, like we're learning a lot about the brain, but at some point we have to sort of, it's public health, right? So this is an interesting thing about, you know, so Jen, you're talking about sort of pre-processing pipelines. There's a million different pre-processing pipelines. You know, the dirty secret is in all these big data things, a lot of the pre-processing is done in sort of a modular fashion, so that you use one software to do this pre-processing, another software to do this pre-processing, a third software to do these pre-processing. Those things interact with each other, right? So it could be that the pre-processing you do after the first one sort of reintroduces the effect of the first. That happens all the time. And similarly, analysis techniques can reintroduce artifacts and confounders that you've previously removed. And it's really a really problematic thing. And so that's one of my fears with sort of deep learning, is that you do all this pre-processing, and then the deep learning sort of relearns the artifacts and puts them back in. And there's big artifacts. In imaging, for example, motion is a big artifact, right? So if people move. So let's say that you take away the motion from the artifact, and then you sort of predict who has ADHD and who doesn't. Kids with ADHD move more than others, right? And so motion is a much bigger predictor of ADHD than brain, right? And so what if the algorithm is learning who moved sort of indirectly in very subtle ways, right? Then you're not really learning anything about the brain, right? You're learning things about the kids with ADHD move, right? And that's the wrong. You're getting a prediction accuracy, but it's not about the right thing, right? And so I think we have to be very careful about that. Causation in the brain, that's sort of the holy grail, right? You know, does activation here cause activation there, cause activation there? I think this is prone to a big, you know, there are these sort of transcranial brain stimulation and things like that's really sort of promising these days. You can sort of kind of zap an area of the brain and either suppress or activate brain regions. If you think that you have some sort of graph, you can sort of basically manipulate sort of nodes in the graph in ways. But this is an engineering problem as well, to get this data simultaneously as you're doing functional neuroimaging. So a lot of these things are going to be partnerships between analysts, engineers, and sort of domain scientists. And those are things that are very important. Figuring out what AI is useful for. So AI is pretty useful for things like normalization and segmentation. We heard that several times today, right? Why is that the case? Well, they're basically relearning an algorithm, right? So basically, normalization is like all our brains are different sizes, right? But in order to analyze them, we need to make them the same. So you take everyone's brain, and you put it onto a standard template so that all our locations are aligned with each other. This is a warping algorithm. And there's lots of these different warping algorithms, but that's basically what they use. You use the original data, you use the warped data, and deep learning is great at learning that transformation. Perfect. Same with segmentation, right? It's an algorithm that they're learning. So it's great for that. It's really bad at developing biomarkers, right? So like, can you predict Alzheimer's or depression or something like that? Doesn't do better than a linear predictor. Why is that? It's probably due to the sample size. And so there's no point in doing it because you're giving up interpretability, and you're losing interpretability with no win. And so that's something that we sort of have to figure out, if there's either sort of a data augmentation thing or something like that. But that's a big bottleneck, right? So it's good for learning algorithms. It's bad for learning things that we don't really understand, right? And I think that we have to sort of figure out why that is. Because, you know, we always want to use the latest shiny tools, but it's only meaningful to use it if it's giving us some benefits, right? So I think we have to be a little bit careful. Last question. What should we statisticians do to get started and accelerate progress? Here I thought maybe I could be a little bit controversial, since we're all statisticians. We can, one thing is, this is team science. Hung Tu, throws out those things, but analyzing 100,000 people is hard. Yeah, you need software engineers, you need computer scientists. You need teams of people to do that. It's not like a solo thing to do. So you have to get involved with teams. You have to access the data, right? So again, having early access to the biobank is important. Having, you can't just wait for the data to come to you. You have to do that. Understand the data. I think even you said this yesterday, like, what do they usually say about statisticians? So we get to play in everyone's backyard. I would say for the last 10 years, that might not be the case. We can certainly play in everyone's backyard, but we don't make any impact. To make impact, you have to understand the data at a much deeper degree. And you can't dabble in things in the same way. And I think it's dangerous to sort of think that you can do that. It's tempting because it's fun to dabble, right? But I think we make our biggest impact when we don't dabble and we focus. So I'm trying to be a little provocative there. And so we have to collaborate across domains. This is hard, right? My best collaborator, I met at Columbia when I was there. We talked he's a psychologist, so we talked for a year. I had no idea what he was talking about. But he was a pleasant guy, so I had coffee with him every week, and so I didn't have very many friends, so it was really nice, but man, I had no idea what he was talking about. And then after a year, I suddenly understood what he was talking about. Now we have 50 papers, right? I mean, so you have to work at it. Get outside your comfort zone. Again, it's not easy talking to people who you don't understand. We're proud, right? We don't want to seem stupid, but you have to be willing to be a little stupid. And then, so this is my last one. I think we do really bad. We don't stick with the problem, right? And so we had this little paper on biomarkers in neuroimaging, and we looked over the literature, 500 studies, and we looked at who actually took their model and then started applying it to sort of independent data sets. 9% of the studies did that. And that's shocking because, and I think this is the problem with getting to the clinic. Like, so what do? We publish a paper in JASA or something like that on predicting Alzheimer's. Once we get our JASA publication, we pat ourselves on the back and we call it a day, right? We don't stick to it. And that's not going to make a biomarker. What's going to make a biomarker is that you then apply that model to data from a different site, on a different population of people. You just have to test the heck out of that model. You have to stress test it until it fails and figure out when does it fail and when it doesn't fail. So there's this whole biomarker development pathway that we largely ignore, right? Because our reward system is to get a publication on this model. Our reward system is not to do all these things, but I think that's the wrong reward system. And I think that, so if I can be a little bit provocative, it's sort of like, it's really nice to make these fancy models, but if we're really going to change the world, we have to get outside of our comfort zone and sort of force the issue, right? Because people are not going to come to us and say, oh, I read this excellent article in JASA. No end user does that. It just doesn't happen, right? We might think it happens, it doesn't, right? So we have to sort of be a part of this and force this issue. So that is my call to this group to do that. And I think that was it. Thank you. Okay. Oh, yes, absolutely. Yes.
Yeah, so, of course, I'm in a stat department. Okay. Of course, I'm in a stat department. It's a much worse situation there than in biostat, as you well know. I mean, in terms of actuating 1 through 6.
Sure.
Right. So, what are your thoughts? I would just love to hear other people. Our whole utility function is so against 1 through 6. It is unreal. I mean, because I really, I want an annals paper, I want or a NeurIPS paper, but to have any kind of impact in real life, I mean, when are we going to get credit? How can you convince your postdoc that they're going to get credit if they actually get a biomarker that might get used? I just would love to hear some conversation about this. It's so frustrating for me.
I'm not saying that I have all the answers here. I think that we're lucky enough to be able to sort of change that. Like, I have tenure, I'm comfortable. I can do that, right? Again, the postdoc is harder. I will say I have two types of students in general. I have one type of student who basically thinks of the image as a matrix and does good math on it. It's cool. I have another type of student who says, I want to understand this, so I'm going to embed myself in this lab of adolescent health and learn about ADHD and autism and do that. That's cool as well. That later group always does better on the job market because they're different. And so I tell all my students, it's like, you might not be comfortable doing that and sitting in this lab, but you're going to do better on the job market, and they do. So I understand what you're saying, but I'm not convinced it's 100% true because people do like to see someone different, right? And those people are different.
I see why Susan asked the question. I actually did 1 to 5.
You what?
I did 1 to 5.
You did 1 to 5. Oh yeah.
But I didn't ignore number 6. Mm-hmm. It's not my fault because when I spent like 15 or 20 years with real doctors. Whenever I speak, they're having a PhD. Okay? so he can publish whatever he likes, but they don't trust what produced. Okay? I trust they produce, but they don't trust I produce. So that's unfortunately, it's not just get out of comfort zone. There is something going on between MD and PhD. Okay? So it's not actually trivial questions. Whether anybody has ability to overcome that question or problems will be an interesting part.
Well, if you want me to be really provocative, you should hear my thoughts about MDs.
Okay. Anyway, my other question.
But this is filmed, right? No.
I think Susan expects me to be daydreaming now, so I'm not going to ask a daydreaming question to you. So if somebody give you $10 million for the next 5 years, and you have a team of 20 individuals, what would you like to do?
I missed the last. I have 220 and.
You have somebody give you $10 million. Okay.
Yes.
And for 5 years.
Yeah.
And you can have a team that you don't have enough, you can have 100 people, say give 20 people that you can build a team, all right? So what would be your question on imaging analysis related to health improvement that a question you feel you can solve and change the field to some extent?
Well, actually, this has happened. So I lead the Acute to Chronic Pain Signatures program. It's an NIH program for studying 3,000 people who transition from acute to chronic pain. So we have a longitudinal study studying people who have an acute pain episode, which is a surgery. And of those people, 20 to 25% are going to develop chronic pain, which is that you have a pain of, say, 3 or more on a scale of 10 after 6 months, right? So a lot of them then become opioid misusers because it's hard to live with chronic pain. So understanding that mechanisms is important. So collecting imaging data, 5 different omics types data, EHR data, patient-reported outcomes. So all the things that we're talking about here, how are you going to sort of combine those into some sort of signature for developing who is resilient to chronic pain and who isn't? So what kind of people do you need? You need a lot of people who can, there's a lot of processing, you need supercomputers, you need software engineers, you need people with domain expertise in each of those fields, because there's so many subtleties involved with EHR data that I don't understand because I don't spend very much time with that, right? So you need all those things, right? And then you can start making a dent in the problem. And you need people who speak different languages. So you need people who sort of speak, a more scientific language, but also a more technical language. And so you have to sort of build on that. I mean, so that's what I do.
So for the interest of time, so thanks for Martin.
Thank you.
We need to